Get it? All right. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Pray to help us to use this time wisely, Lord, and just to glorify you and what we do, Lord. In your name I pray. Amen. All right, so let's see here. So I asked to calculate the divergence of this pesky vector field, and right. So basically, partial p, partial x works out to what? So partial p, partial x here, after the dust settles, what we got is we've got y minus b quantity squared minus x minus a quantity squared over x minus a quantity squared plus y minus b quantity squared all squared. On the other hand, partial q, partial y, through very similar calculation, works out to x minus a quantity squared minus y minus b quantity squared divided by the same denominator. Both of these are by the quotient rule and the chain rule. So when you add these two expressions together, what do you get? A big fat 0. Now, this is not surprising. What this problem is we did this with a and b both 0 the other day. So what this is saying is that if you shift the reciprocal vector field to a point a comma b, it still behaves the same. In other words, if I was to draw a picture for this thing, the field lines, if this is a comma b, the field lines are kind of like this. It's supposed to be lines. There's some kind of irremovable badness at a comma b. F of a comma b is undefined. There's a singularity there, that's right. But the divergence is everywhere else 0. So if field lines are coming from anywhere, they're coming from a comma b, is what that means. Right. All right, so then problem 2 was to discuss what's the flux of this vector field through any curve which does not contain that singularity. And the point is, whatever the curve looks like, if this is a comma b, right, you can envision the field lines like so, right? Here's some of them. You know, whatever, they fan out from here, symmetrically so. But you see what happens. Any field line which comes into one side of the curve, it goes out the other. So whatever comes in comes out, which means that the net flux should be 0. And that's what Greene's theorem, the divergence form of Greene's theorem, verifies. See, because the flux through the curve is the integral of the two-dimensional divergence over the area, which we just calculated to be 0 over here. So the flux through that curve of that vector field 0. Now this was much nastier, because now I said, well, what if the singularity is inside the curve? Then what's the flux? All right? So we'll come back to that. This one actually is easier to understand if we've done problem 4 first. So problem 4, I said, suppose you've got this identity. Well, I guess it's not, well, I've got a couple different ideas competing here. Oh, fine, I'll just take my medicine and talk about problem 3 to start with. So the idea here is I cannot, if I have the region that includes the point a comma b, I can't use Greene's theorem because the vector field's not defined there. So what I got to do is I got to like bubble around the place I don't understand and work on one side or the other of it. So what I suggested Rip can do is to look at a little circle of, say, radius r, which contains the point a comma b like that. And so if you do that, you can break it into two pieces, an upper region and a lower region, both of which we have the divergence of f is 0 in here, and we've got the divergence of f is 0 in there. The point which is misbehaving is outside the regions, so I can apply Greene's theorem to either those upper or lower sort of half-annulus, if you like. And what I was trying to point out, but as you guys are often tempted, you get into the details which don't matter. Sorry. The boundary, that last thing you wrote was probably useful, sorry. But the boundary of the upper region, and the boundary, well, the flux through the boundary of the lower region, so the R up and R down, right? Well, what does that give you? That gives you the flux through C, right? But also, you have these cross cuts. So over here, I've called the cross cuts like C3 and C4. Similar idea. So let's say, I'll keep with my labeling, C3 and minus C3, C4 and minus C4. Although the picture might be slightly different. Nope, same. Okay, so the point is the flux through C3 and minus C3, they're equal and opposite, right? The flux through C4 and minus C4, they're equal and opposite. Whatever goes out of one goes into the other, so they're just balancing. And then, but on the other hand, we have the flux through the outer piece, and we have the flux through the inner circle. Now, the inner circle, I should be careful. How's that oriented? This is actually oriented clockwise. It's a clockwise oriented inner circle. All right, so, okay, so this, remember, would be equal to the integral, the double integral over R up of the divergence of F, double integral over the down region of the divergence of F. The thing I'm after, right? And then here, plus the integral over the counterclockwise oriented circle of radius R of F dot the normal ds, the flux, if you will, through the inner circle, counterclockwise oriented. So this 0, this is 0. So what this gives us is that the flux through the circle is actually the same as minus the integral over the clockwise clockwise. I said CCW, I meant CW. Sorry. I know there's no kind of romanticism / teen angst or anything here, but nevertheless, CW. Let's see here. So CW, CR. Oh, I'm sorry, you guys don't watch TV. Never mind. Let's see here. F dot n hat. You know, I used to watch Smallville once upon a time. That's a real show on that network. And then something happened. But actually, Smallville got stupid at the end too. I digress. But kind of a dark turn with the Smallville actresses in the end, right? But anyway. So, yeah. Recently. So, counterclockwise oriented CR of F dot n hat ds. I digress. So if I reorient the inner circle to be counterclockwise oriented, then I have the flux of, what I'm trying to tell you is that the flux through this inner circle, counterclockwise oriented, is equal to the flux through the outer loop, counterclockwise oriented, because the divergence between those curves is 0. This is an example of the deformation theorem. If the divergence of a vector field between two similarly oriented curves is 0, then the flux through the inner curve is equal to the flux through the outer curve. You could do it for both of them being counterclockwise, or you could do it for both of them being clockwise if you wanted. So then the question becomes, well, what is the flux of this particular vector field around a little unit circle? By the calculations we did yesterday, it's 2 pi. Because this is nothing more than the reciprocal. I mean, if you want to, I could build a system of modified polar coordinates based at the point A, comma B. And this is really nothing more than the vector field. I mean, anyway, this is 2 pi, if we were to actually work out the details. Because you see what this is? I mean, I need some place to write, but I'm going to just erase all this, actually. Look, this, if you were to define modified polar coordinates, x equals to a plus r cosine theta, y equals to b plus r sine theta. Start your coordinate system based on this point rather than the origin. If you were to do that and so define, theta hat to encircle the point a comma b, then with that definition, f is nothing more than, it's really nothing more than 1 over r theta hat. So when we do the integral over a circle of radius r centered at a comma b, what this is, f dot, oh, I'm sorry, that's not theta hat. I'm an idiot. Help me out, guys. What should that be? Yes, it's r hat. Thank you. So theta encircling r hat, like this. Modified r hat, really. Then this calculation would just be the same as the integral of r hat over r, because we're on r equals to r. And then the n hat is r hat and ds, so you get 1 over r integral of ds over the circle of radius r, which of course is 1 over r times 2 pi r, which is 2 pi. Alternatively, you could actually parameterize the circle and go through what Ripken was starting to do, which would have been to actually straight up calculate this, which you could do, and you'd also get 2 pi. It would just take longer to work through the details here. I'm just trying to get you guys to see past, like we can move this example that we have at the origin of the reciprocal field that has divergence here everywhere except for the origin, and we can move it to another point, and we could still have the same storyline based on whether or not our loop included that point where the thing is centered. So 0, 0 being the interesting point is just an artifact of us using the one we looked at yesterday with x squared and y squared rather than x minus a and y minus b squared. Any questions about this before I go on? So this is going to seem like a repetition of what I'm about to do, because it's actually the same problem, recast a little differently, without the pesky extra 2 pi calculation in the middle. All right. So over here I said, explain why the identity partial q partial x equals to partial p partial y for that vector field implies that these integrals are equal. And I, shame on me, I meant to give you the following picture. C1 and C2 are 2 loops, similarly oriented, either counterclockwise or clockwise. Let's say counterclockwise for the sake of discussion. So if that's the case, what you can do is you can take these 2 loops and you can put in some crosscuts like this. So crosscuts in the sense that this one goes this way and that goes that way. Goodness gracious. Oh yeah, and this way. That way. Now, that doesn't change anything, putting in those crosscuts, if you add the integral along both of them, because they're reversals. So like adding the integral along C4 and minus C4 and C3 and minus C3 does not add anything. We can add the integrals over the crosscuts without changing anything. So why to do this? The reason to do this is so that we can apply Greene's theorem for a simply connected region on the upper half and the lower half separately. See, the upper half, R up, is a simply connected region. It's got no hole. The lower half, R down, it's a simply connected region. It's got no hole. So we can apply the Greene's theorem that we derived yesterday. Well, yesterday? What's today? Friday. The weekend doesn't count. See here, nothing interesting happened this weekend, right? So, there's the tornado, but ignoring the tornado, of course. My urgent care now needs urgent care. But, yeah, that happened. So this is heuristically, like, that's nice, but this really should be the integral over the boundary of R up of P dx plus Q dy equals to that. That's what I was, so I'm sorry, I set you up. I meant to put like colons here, like think about this one, think about that one, but we actually have to think about the integral over the line, the boundary of P dx plus Q dy, right? Now, I gave you the identity that partial q partial x was equal to partial p partial y, right? Which is to say that those are 0, right? And so what's this give us? This gives us that the integral over the upper region and the integral over the lower region sum to 0. But how, oh, I'm sorry. Now I remember what I was trying to tell you to write down. And I'll write it down for my, oh, I'll write it down. No trouble here. So what is R up? The boundary of R up is what? It's got different pieces. First of all, it's got C1 up. This piece. Right, that guy. Then it's got minus C3. Then it's got minus C2 up. The minus because you see the boundary of the R up has to be counterclockwise for R up. And so counterclockwise for up means that when you get to this side, it's going like that. But the original C2 wasn't going like that. It was going like that. So it's the opposite, the direction of the given. Oh, good grief. That's the worst. Sorry. If I hadn't noticed that, and I like half used this one place and didn't use it another place, I'll tell you it would have been bad. Anyway, so that's minus C2 up. And then continuing, so we got our minus C3, minus C2 up, and then finally, minus C4. That's my R up boundary, right? What's the boundary of R down? Well, R down, let's see here. We've got, I'll start with C1 down. Union with what? So here's my C1 down. And then I get C4. Right? I get minus C2 down. And then I get C3. So I know that the integral so let's see here. What do I have? I have that the integral of f dot dr over the boundary of the down region plus the integral of f dot dr over the boundary of the up region is equal to what? 0 plus 0, right? Also known as 0. But when I add these two together, I really have what? The integral over, f dot dr of what? The union of these two things, right? So what happens when you union these two curves together? What are you left with as a point set? What you're left with is C1. Yeah, C1 minus C2. See, because the crosscuts, when you put the two curves together, they just cancel out. Those just cancel out when we look at the combination of the integrals. And so what you're left with is that this is equal to 0, but then this is the integral of C1 f dot dr plus the integral over minus C2 of f dot dr equal to 0, which then, of course, tells me that the integral over C1 of f dot dr is equal to the integral over C2 of f dot dr, which is what we were trying to show. Listen, you don't have to go through this derivation anymore. We've gone through it together. There's a larger intuition I want you to take with you here, which is that when we have two curves, right, which bound some sort of annular region, there's some region between the two curves. One curve forms the inner boundary, the other curve forms the outer boundary. When partial q partial x equal to partial p partial y between those two curves, what do we get to say? We get to say that the line integral around those curves, those boundary curves, are equal. The thing I just erased says something related. It says that if you've got two curves like this, right? If this is C1 and this is C2, and the divergence of P comma Q is equal to 0, then what do we get to say? The flux through C1 is equal to flux through C2. That is a related but different result. The divergence being 0 between the two curves gives us that the flux is the same through each. Whatever goes into the inner curve goes out, goes in, well, whatever field lines pierce C1, they also have to pierce C2, basically. This, on the other hand, is a different condition, right? This is not that the divergence of the fields is 0 between these two curves. It's what? It's actually the two-dimensional curl, if you will, being 0. I put some quotes because I really only wanted to find curl for a three-dimensional vector. So if you want, it's the curl of p comma q comma 0, which is 0 comma 0 comma partial q partial x minus partial p partial y. When that's 0, we get that the integral over C1 is equal to the integral over C2, which is what I call this theorem here, I refer to as the deformation theorem. All right, well, enough about that for now. I try to explain, but I know this is a difficult concept I'm trying to communicate to you guys right now. Classically, this gives you guys a lot of trouble sorting out these ideas. All right, so this next example is much friendlier. This is just a plain Jane Green's theorem problem. I have this integral over the rectangle. Calculate the integral, right? So this should tell you, since we don't actually know how to integrate tangent squared or inverse hyperbolic cosine of the exponential plus 17, I mean, maybe you could do it, right? But, I mean, I might be able to do it. I don't know. We use Green's theorem. So this question mark is equal to that by Green's theorem, because this is the integral over the rectangle of what? We're looking at partial q partial x here, right? Minus partial p partial y, which is over here. So partial q partial x actually just works out to 1. Partial p partial y works out to 2y. So that's why we get 1 minus 2y. And for some reason, you guys are, why are you guys so stingy on your parentheses? This is so much. Gotta drive me nuts. So parentheses, yes. But let's see, I probably believe you after that. X, right, so that's a 3 minus 6y. Yep, we good. And then that's 3y minus 3y squared, value from 0 to 2, which gives me oh, 6 minus 12. Otherwise known as minus 6. Yeah, what's that? Oh, yeah, I guess so. I mean, fine, whatever. I give up. I admit it, I love parentheses too much. But I know you guys love them too little. So somewhere in between there's the right balance.
CS folks love them way too much.
Somewhere. CS folks? Well, I guess you got no choice. You had to talk to something as dumb as a machine. little choice to be, you know. What's that? Oh, the last one. Yeah, we've worked that out like 3 times now. So this one here, this is, again, the reciprocal vector field, this time centered at 0, 0. What are we looking at here? I guess I don't disagree with that's it in polar coordinates. Right. I don't know what this is, though.
Me neither.
So, oh, yeah, that's not how it works. I mean, that algorithm we did, integrating first with respect to x and then with respect to y, that's for Cartesian coordinates. If you were to try to sort through polar coordinates, you need to do it with respect to the polar gradient, which has got a little bit more fine print. So let's not do that. Instead, let's just, recognize that this, again, is 1 over r hat, right? And so if we were to integrate over the unit circle, or just, unit circle, for example, however you want to do that, this would be 1 over 1 over r hat dotted with, n hat ds. Well, in the unit circle, that would just be the integral over, x squared plus y squared equal, however you want to denote this thing, but r hat dot r hat ds, and so that'd be 2 pi. But the larger point here is, we worked this out in more careful, detailed previous lectures, but the point is, if you look at any circle which centered around the origin, you can look and prove that the integral around the loop is non-zero, right? Which means that the vector field is not conservative, because that's one of our list of equivalent conditions for conservative, right? Let's see here. But I admire the attempt to just straight calculate the potential. I mean, maybe that's worthwhile. So you're trying to think f 1 over r hat, right? Is that equal to the gradient of some, let's say, phi? Oh, fine. Let's say f, right? Now, this, in polar coordinates, what is that? That's partial f, partial r hat, plus 1 over r, partial f, partial theta, theta hat. So this tells us 2 things. This tells us we need to solve partial f, partial r equal to, well, 1 over r. And we need to solve 1 over r partial f, partial theta equal to 0. Interesting. So that would suggest to me that f is equal to minus 1 over r squared, right? Times what? If I integrate the, oh, I'm sorry, I can't do math. What's the integral of 1 over r? Idiot. Me, not you. Yeah, log of r plus some, constant, which is possibly a function of theta, right? Huh. Mysterious. So, when I feed this to the other condition, I need what? 1 over r. What's partial f? Well, I get, dc1 d theta equal to 0. Which suggests if we make c1 a constant function of theta in a void where r is equal to 0, it seems like f equals to the natural log of r will work. Huh. And yet I know it doesn't, because we just calculated the integral all around a circle is 2 pi, which proves it's not conservative, which proves that that potential cannot derive the force field on the deleted plane.
assuming that R is not 0.
Yeah.
Calculation. So would removing that discontinuity enable us to still calculate something?
Wait, why is R not 0? What is that domain?
Yeah, if R was 0, you'd be 0 in the original.
Oh, so that what I said doesn't make sense then.
I mean, we just showed that the integral of this vector. Is that right? Oh, I'm sorry, guys. I'm an idiot. I'm so sorry. We're supposed to show that the integral around the loop. I have. I'm so sorry. I'm so sorry. So that shows that the circulation. No, excuse me. The flux. That shows that the flux of F. The flux of F through the unit circle is 2 pi. What's the circulation of the vector field through the unit circle? That's something different. So the work done, or the circulation, we have two different concepts at play here, guys. So the circulation would be an integral over the unit circle of, 1 over r hat. What's dot dr? So dr vector is really, in this case, theta hat ds. But of course, I mean, and you can see this. This is the radially outward vector field. The tangents to the unit circle meet it perpendicularly, right? So the work done as you go around the circle is 0. So this is equal to 0. So what we're struggling with right now, guys, what I forget about sometimes, my bad, is the integral of p dx plus q dy versus the integral of what? What's the formula for the flux in terms of p's and q's? What was it? You have to tell me because I forget. All right, so these are not the same thing, right? This gives you the circulation of PQ along C, and this straight up gives us the flux of the vector field through the curve C. The theorem we had about conservative vector fields does not concern flux. Not directly, at least. It concerns work done, or circulation. The work done is 0. And in fact, this calculation is legit. That is the potential. This vector field is conservative. And here you go. This is its potential. So in fact, I shouldn't have poo-pooed what you had written. I should have accepted it. I think. I'll have erased it. I'm not sure what it was now. Did I talk?
He said it wasn't conservative.
Oh, he wasn't conservative. Okay, well, you shouldn't have told me that. We could have, now that I've erased. But yeah, I think it is conservative. And in particular, F, the natural log of the square root of x squared plus y squared is its potential function. That's defined on the punctured plane, and the gradient of that gives you back the vector field again.
What if we didn't convert this to Poland? Is there a way to get that?
Yeah, I think if you were to solve partial f partial x equal to x over x squared plus y squared, and partial f partial y equal to y over x squared plus y squared, I think there's a shot. You should have a shot at that. I mean, integration, let a u equals the denominator. That should be an I mean, that integrating this with respect to x gives us the natural log of, x squared plus y squared times a half, right? Plus c2 of y. Yeah, I think we can do that. That half makes it into a square root, yep. The mission. Well, I mean, you guys, how is the progress of the class on it? No one has much asked me questions. Yeah.
My birthday's tomorrow. Can we do Wednesday?
Sure.
Mine is due. Wait, Ian, mine is due. I didn't say.
I will. Oh, wait a minute, your birthday is Wednesday.
Mine's Wednesday. Oh, we can't have it.
Oh, well then it has to be due Thursday then. Yeah. There you go.
Is it actually? No, it's,
Yeah, Thursday. Thursday's fine.
it's not actually.
Wednesday it is then.
Wednesday?
This is a roller coaster of emotion, isn't it? Let's stick with Thursday. Thursday's fine.